Okay, let's start by shattering a pretty common illusion right out of the gate. We often think of computers as these incredibly smart, intuitive machines, almost like magic, right? But the reality? They are painfully, meticulously literal. A computer is essentially a brilliant speed reader with absolute zero common sense. It relies entirely, and I mean 100%, on the precise sequence of instructions that you, the programmer, give it. If you've ever had a program just crash out of nowhere, freeze up, or spit out complete nonsense, well, you've experienced exactly what happens when that sequence breaks down. So today, we're mastering the literal backbone of code, instruction sequence.
So in this explainer, we're going to cover why order matters, meeting your program objective, the 3 sequencing errors, avoiding sequencing errors, and finally putting it into practice.
All right, part 1, why order matters. Let's anchor our understanding with 3 key concepts. First up, sequence. This is simply the exact order in which instructions are executed by the computer. Second, the objective. That's your end goal, what the program is actually trying to achieve. And finally, flow of control. Think of this as the specific path the program takes during execution to reach that objective. You really have to remember this. The computer never guesses your intent. Unless you explicitly use a control structure to change it, the machine is just going to follow your instructions exactly in the order you wrote them down. Here's a perfect example of what happens when you ignore that golden rule. In a correct sequence, the first step gets the name from the user. The second step creates a greeting message using that name, and the third step prints it out. It flows logically, right? But what if we mess up that sequence? If our very first step tries to create the greeting message using a name variable before we've even asked the user for their name in the second step, everything breaks. Trying to use a variable before the user has entered it causes an immediate error, simply because that value literally does not exist yet. Input absolutely has to be collected before any calculations or concatenations can happen. Moving on to part 2, meeting your program objective. Let's walk through a real-world scenario chronologically. Say our objective is to ask for 2 student marks, calculate the average, and then display whether the student passed or failed. Steps 1 and 2, get mark 1 and mark 2. Why? Because the program needs that raw input before it can even think about doing math. Step 3, calculates the average using those 2 stored inputs. Step 4, checks if that average is greater than or equal to 50. You can only make that decision after the calculation is fully complete. And finally, step 5, displays the pass or fail message. Output always comes after processing. Input, calculation, decision, output. That right there is the perfect flow of control. Okay, part 3, the 3 sequencing errors. Our first monster is incorrect output. This happens when the program runs completely. It doesn't crash at all, but it gives you the wrong answer. This one is incredibly sneaky because it finishes without throwing a glaring red error message. It might actually look correct at first glance. This usually happens when a calculation is placed just before a variable is properly updated, which is exactly why tracing your code line by line is absolutely crucial. So here's a quick puzzle for you. Let's say step 1 sets a price to 40. Step 2 calculates the discounted price by subtracting the discount. Step 3 sets the discount to 5, and step 4 prints the result. Can you spot what went wrong here? If you notice that the second step is jumping the gun, you are spot on. In the faulty logic, the discount variable is being used in the math before the program ever assigns it that value of 5. The intended logic is all there, but the broken order totally ruins it. In our corrected version, we assign the discount to 5 first and then perform the calculation. Values must be assigned before they are used in any kind of calculation, no exceptions. Let's look at our second error, the infinite loop. This is when the program just repeats itself forever and ever because the loop condition never actually becomes false. It doesn't just stall your objective, it leaves your computer sprinting on a digital hamster wheel. It wastes massive amounts of time and processing power, entirely dragging your performance down. Let's see exactly how this trap is set. In a faulty loop, say we start with a count of 1, and we tell it, while the count is less than or equal to 5, print the count. But wait, the count never actually changes. It will literally always be 1, so that condition stays true forever. The missing piece of the puzzle is the update statement. A corrected loop adds a crucial line at the end telling the count to increase by 1 each time. The big takeaway here, when building loops, always double-check your starting value, your condition, and your update statement together. Which brings us to the third and final fatal error, deadlock. Now, this is less about a single line of bad code and more about concurrent or multi-threaded systems. Deadlock happens when two or more processes are waiting for each other, and because neither one will budge, the whole program freezes completely. Imagine a classic standoff. Process A has locked up resource 1, and it's just sitting there waiting for resource 2 to finish its job. But process B has already locked resource 2, and it's waiting for resource 1. Process A won't let go of its resource until it gets what B has. Process B won't let go until it gets what A has. It is a total, unresolvable standstill. So how do we fix this? Well, you can arm yourself with a few pro techniques to reduce deadlock risk. First, always acquire resources in a consistent order across all your processes. Second, use timeouts or lock limits, meaning if a process waits too long, it's forced to just let go and try again later. And finally, always release your resources as soon as you are done with them. Don't hoard memory or files when you don't need them.
Part 4. Avoiding sequencing errors.
Believe it or not, writing flawless code actually starts before your hands even touch the keyboard. Look at these before coding habits. First, write your objective out clearly. Then list your steps in a logical order, just like we did with those student marks earlier. And most importantly, identify exactly which values are needed before each step can actually happen. Good planning is basically your best defense against bad sequencing. And when you're actively typing, you want to maintain these while coding habits. Use incredibly meaningful variable names. Seriously, don't just name things X and Y. That's how you get confused about what data you're even working with. Indent your loops and decisions clearly. Having clean visual formatting makes spotting a sequencing error so much easier. And, like we talked about, relentlessly check your initial values, conditions, and updates. Finally, your after-coding safety net, testing. Trace the program with sample data just to ensure the sequence actually matches your logic. You want to test it with normal inputs, edge case boundary inputs, and even completely invalid inputs to see what happens. And if something looks a bit off, use simple print statements or a software debugger to trace the exact execution path, line by line.
All right, part 5. Put it into practice.
Let's test this all out. Here is our objective. We need to get a radius from the user, calculate the area of a circle using that radius, and then display the result rounded to 2 decimal places. That's the exact flow of control we need. But look at this. Our instructions here are totally jumbled up. Right now, it's trying to print the area, then get the radius, then calculate the formula. Treat this like a quick puzzle. Mentally arrange these 3 steps into the perfect logical sequence based on everything we've talked about today. Which one has to go first? Okay, let's see how you did. Here's the correct sequence. Step 1, we have to get the radius input first. Step 2, we use that radius in the calculation to find the area. And step 3, we finally print the rounded result. Input has to happen before the formula is used, and the calculation must finish before the output is displayed. Simple as that. You've seen exactly how crucial order is today. So I want to leave you with this final provocative thought as we wrap up this explainer. What error would actually happen if we tried to print that area before it was calculated? Would we just get an incorrect output, or would the entire program crash because the value doesn't even exist yet? Think about the painfully literal nature of the machine. The next time you write a line of code, ask yourself, does the computer have everything it needs to execute this right now? Thanks for joining me on this explainer, and happy coding.